Hi, welcome to the lab. So, in the last video, we started working on turning our non-deterministic finite automaton into deterministic ones. And to do this, we are going to use a well-known algorithm, which I mentioned in the last video, but I didn't mention the name. So, it's called subset construction. And basically, you track which states your non-deterministic automaton relate to your states in your DFA, and you do this by simulating all the non-deterministic finite automaton. So sorry, at once, and you see which state is reachable, and those you combine into a DFA state, basically. So, and we're going to do this a little bit differently today, I think. So, since the last video, I slept really well, and I think I know how to implement this now. And I think in the first step, I'm going to introduce a very simple map class, since I need to associate sets. So I'm just going to create a class called map, and but a map, of course, has a key and a value type, and to add a key value pair, you can just I also introduce a move. I'm not really sure what this means. So I think let's just add it to our list. So, and since I'm doing the dumbest build possible, we're just going to add we're just implementing our map as a list of pairs, I'm thinking. So key and value. So a list of pairs. And let's also remember a set of keys. So then the iterator iterates over keys, and to check if contain a key, we can just ask our set. Now we just got to implement add methods. So to add the value pair, so if we already know the key, we don't do anything. What else? We add it to our keys map. Let me just fix the name. So to edit, we just don't know. Hello. So we're adding the key and we're adding a value pair to our list. And the same here. So if we already know the key, so let's just drop the second overload of add. And we need a get method. So let's do, so we don't have an option. Let's do something like this. We want to read a value, and we would like to find this. So basically we are writing the return value, and this one won't change our state. So let's do a very stupid implementation. So this is the gist of this class. It just provides an API, which is really stupid. We're going to fix it later, but just want that it works, and yeah, well, we can later turn it class into a hash map or to a fancier map. So so if we don't know the key, then we just return false, and otherwise we should find our element in the list. So for iterate over our list, and then we should find a pair rows equal to key. And in this case, we're just going to return true. And also we are assigning the value to our result. So this should work, and this case should be impossible. Unreachable. Otherwise we made an error when implementing this. So this is a really stupid map, but it should work. So I'm not going to test it individually. So then I would do the following refactoring. So we have a map, perfect. So then I would like to re-implement this method. Oh. I think I'm just giving it a set of NFA states. And so let's keep the old implementation as a reference. So what do I want this method to do? I would like to do the following. I would like to give it a set of states. I think as a, well, I don't really care. A const reference should be fine. And I would like to do following. So basically, this method so basically we do the following. Let's draw. So, for example, we have the following automatons. So, for example, we have the non-deterministic automaton A, for example. Now I'm using distinct names for the two automatons. So using characters for this one. Or let's say this is our automaton. Let's do another one. And here, for example, B. So let's say we have those two automatons. So we don't really see that this one is in A, but doesn't really matter. So to create an DFA state while simulating those two automatons at once, we're going to create a set of states with the start states of each of those. So in this case, we have a 0 and an A. And this is what this method gets as an input state. And basically, it should return a set containing all states reachable via epsilon. And it does this iteratively. So we just start by with 0 and A. So I think I'm just going to type this out while I'm explaining it. So that was beautiful. So I'm creating a result set. And first of all, I'm going to okay. I'm just adding all the states we already know. Then we iteratively expand this step by step. So we simulate each automaton. So basically, in the first iteration, we look at this state. So since it is here, and we see which states are reachable via epsilon, and this is of course 1. So then we basically remember that we already, this state is handled, no other state is reachable by epsilon. And then we deal with the second automaton. And here B and C are reachable, B and C. So this is the first step of the iteration. Then we start it again. And now basically we are looking at the new states and follow them, which states are already, which are reachable from those new states. And in this example, no state is reachable. But for example, if we had a back edge here, then in the third step, the state A would be added again, since we follow this edge as well. But of course, A already handled A, so we don't really, yeah. So basically, we expand our initial set of states and add all states iteratively which are reachable by epsilon, starting by our first steps, the first state. So basically, in this case, we iterate so we change this, we iterate over our result set and look which states are reachable. We remember them in this set, and then we adding them in our result set. And if we didn't see them already, we add it. And remember that we modified our result set, and then we keep repeating until nothing gets modified anymore. So, and then we just return our result set. So now I can remove my old implementation. So and now this works a little different. I think I can just pass this set in and assign it when it comes back. So I think to create a DFA, we gotta start like this. Ah, yeah, I see. So now, okay. So this just creates a new Dfa state. So I think I have to restructure this as well. Well, but I need to start with a start state. I think this should be fine. And so now we need to map from NFA states to DFR states, I think. The other way around, it is possible, since our DFR state contains all NFAs. So I think to create a map which takes a set as a key, this is going to be efficient. A set of NFA states gets mapped to one DFA state. So let's just give it a stupid name. So and I need to include our stupid map. And I did also forget X. These should include. So how I'm going to do this. So this one stays the same. So basically I have to do what I'm doing here. Then I can expand epsilon. This is the resulting NFA state set. This is fine. And this is the start state. So now I have the start state of the new DFA, in which in this case, this would be this state combination. And then I have to see which states are reachable. But the hard part, I have to merge ranges. I see. Okay. Can I express this a little bit better? And also, I don't know if this works, since so those are simple values, just have 2 pointers in it. So I can always make a copy out of those, but I can't always copy DFA states. So let's fix our map. I think our get method is not really correct. So let's say our get returns an option. We don't have options. Let's just say it always returns a value reference. A mutable value reference, since I'm needing this now. So, and let's just assert that we contain this key. And then I'm just going to return the reference to this storage. And yeah, I should also be asserting here. So this method now works, I think, as I intended to work. So now I can always take a reference of this value. So I think I can change this. So this code, let's just clean this up a little bit. So let's just say let's just build a method which is going to return a Dfr start state, and it accepts the list of NFAs. And I think it will also return a, well, let's just see what we actually need. So, and this does the following things. Basically, it does the following thing. Returns the state, the Nfr start states. We're just constructing the list of Nfr start states, Nfa start states, and then we need the mapping as well, and let's just pass it in. And I think we also need our DFA builder. Since now I do the following thing, I can do a Nfr States in epsilon expand epsilon, the list of Nfr start states. These are the combined state, the epsilon expanded start state. So now this is a set, isn't it? It is. So now I can basically do this code. I can look this up. We didn't already see this. So I need a equality operator on sets. Let's just introduce it, but I'm going to implement it later. So operator Boolean is the return value operator. So we get a set of the same type as an argument, and we are to answer if we are equal. So, and also let's just add the unequals operator, the inequality operator. So, and I'm not going to implement this now. I'm just going to assert false. Just compile, and it's just always return false. For now, so because we should never reach this return, we should always crash before. So now this compile error should go away at least. So if our mapping doesn't contain our new state, we're going to create a new mapping. So we're going to add a new Nfa state. What does this class need? Of course, our set of states, but also the DFA state, so the real state, so to speak. And this one we are just going to create. Dfr create state, passing it in, adding this to the map. So we are mapping our NFA states to our Dfr state. And we are, of course, we are returning NFAs. No, we're returning the internal reference from our mappings. So, and if it is, if this is already contained, I'm thinking I'm just going to do this every time. So in this start state, this state is the start state. So I think I can just configure it as the start state. So this should be fine. So now I can refactor this. Just a call to this. So I'm passing in my DFA builder, my mapping, and the list of NFAs. NFAs. Wait. So see if it works. Run it. And of course, I didn't implement. What did I miss here? So of course, it fails in our equality operator. So I think I have to implement it. So when are two sets the same, and I'm going to implement the performance, the most fast, the fastest, the most fast, scuffed fast implementation. So basically, if ours, do we have a size? We don't have a size. Well, we can just expose it the size. So we're just going to compare the size of our current map, and if it is not the same as the set we are comparing to, then we are can't be equal. So else, the following thing: we iterate over all elements this map, and if if this element is not part of the other map, we return false. And similarly, we also check every element from the other map, and we check if it contains in this map. So this is the worst implementation of a set, but I think it should be okay, since the ordering of my elements doesn't really matter, since a set is an unordered collection. I first of all check if other contains every element from this, and if this contains every element from other. But I think I should unstref those. No. Not fast, but it should work. So, and I forgot a return value. Ah, yeah. So we have a crash here. We have to return anything. Let's do the following. Let's remember our pair. Let's just remember our pair here. And let's just return this here. So it should of course crash, but now we have a return and we are working around the compiler warning, the missing return value. So now it should build and it should run, but the map, well, map line 60. So we reached this one. Why? Huh? Let's see. So we get called a set of 5. Oh, I'm dumb. So this assert now doesn't exist anymore. So sure. Okay, cool. Now we have a DFA start state again. So now not sure how exactly we're going to proceed now, but now I think I have to go through all possible characters and simulate this state, which basically contains a lot of. So I have to find a list of states which is reachable by this. Position. So let's see. Nfa State here. This one, reachable by epsilon, the name epsilon. And I'm thinking to repeat this method and give it a character. So just going to copy paste it. reachable by character, and we give it a character. And then so we basically have to do one step, I think. Don't have to do epsilon in one go. So we're just iterating over our states. And we look have a look at which are reachable. And we collect every state which is reachable by the character. So we skip epsilon transitions. We skip transitions which are not, and we skip transitions which are not reachable by this character. Yeah. There's a new 8 here. So we collect them all in our list. We're just going to return them. Okay, sure. So now, how do we do this? We could use a queue data structure. We can use an index. So I think I'm just going to do the following. So we are constructing, we're always starting at a state. In this case, the only state we added. Can we just store a list of states? I think we can. So we are using a queue-based algorithm. How do we do this? So this one only is a temporary reference. So the DFA state this pointer is stable, the state of our DFA state, but then I have to search every time. So let's use this. Let's not overthink it. So this is our list of, this is our queue basically, our states, Dfr state queue. And we insert the Dfr state of our start state. So now we can just do a queue operation. So while we're using an index, so and we need to store let's just let's just do something. So basically, the idea is we're looking up the first state in our queue, or Dfa state from our Dfa state queue. So we're handling this state. I think I can just use I is less than the length of this queue. So process this Dfa state, we have to do the following thing. I have to check which character is reachable. So is the last one inclusive or exclusive? Inclusive, it seems like. Okay, sure. So now we have to check which state is reachable from this state using this character. So we do a states, let's call it reachable, and we just following. We first find which states is reachable by this character, and it takes a Dfr state and now I have to look this up. So now I have to look up the corresponding Nfa state. So let's just do how do I do this? So I'm just thinking, this has to be a stable pointer, but it isn't in my map since it can be relocated. So what if I just allocate Dfa states on the heap and remember pointers? Then I can reference them from anywhere basically. So let's do this. I don't love this, but let's store those as pointers. Then I can also just return pointer here. And here, of course, I have to allocate it on the Okay, so then this one is a... Oh, and then I can just put those into the queue. Perfect. All's really nice together. So then our queue doesn't contain states, but DFA states. So, and then I can just say NFA states. Yeah, reachable by character, so I give it a character. And then I have to epsilon expand it as well. So reachable by epsilon. So think like this. So then I get a set of states which are reachable by this epsilon. And now I got to check if we already have such a thing. So if our mapping already contains this set, and if it does, so maybe we start with the obvious case. If it does not contain it, then we create a new one. So basically, we repeat this process. And this is the reachable state. We add it here. So this is called reachable. So in this state, we didn't handle yet. So we have to add it to our queue as well. So Dfr state queue add new state. Okay. And if we didn't add it, we already had it. So then I have to find an arc, basically. But now, so now I just get the state. So this is the old state and this is the new state. Sure. And I can just get it. New state. So this is a new state. And now I can basically, so let's just sketch it out. I would like to do the arc. I have a find arc. I give it my automaton and the states. Let's say get or create arc between. Let's say a really really long name, but I think it's really expressive. So then we're just, so this operation should not fail. So either we already have an arc between those nodes, or we're going to create a new one, and then, so let's annotate it by arc, just so that I can keep typing, and I'm going to implement this method in a bit. And then I'm just going to add char set, the character to the char set. So that. So we just remember that we have another, we include this character in the existing transition, or could also use a different transition. So, and here, I think I'm just going to implement this one inline. So we're just going to search our arcs from our DFA. So, and if our arc links Nfa state and new state. So if our arc links those two, we're going to remember this arc and break the loop. And if our arc between null pointer, we're just creating a new arc. DFA, create arc between this and so I think this should be it. So this can be I can turn this into a for loop. I just saw that I introduced an error here. So this loop variable is called C. I have to use it in this loop as well. Okay, sure. Let's just read it again. What I dislike, of course, that this code, the same, basically the same. So I think I should. How does it work? So okay, if we introduce a new state, where do we do this? Here we add it to our queue. So then we will handle this in the next iteration. And then we have to flag each state accepting. Ah, yeah, I see. So this state, when this state is accepting, so can I do this in one go? So basically we would like to set this flag. And we do this by just looping through all NFA states. If one of the NFA states is accepting, so Dfr state, we loop through all NFA states. So this one is a NFA state. And if our NFA state, the NFA state is accepting, then we remember that we are accepting when we can then break the loop. So if at least one NFA state is accepting, the Dfr state also accepts. So, and then I think we have an NFA, a DFA, of course. So let's just return our DFA. Look and see what happens. So let's just return our DFA. I print it. I can't print it. Just copy this code. So can't I just print it? ignore the I'm remembering that I had a problem before, but I don't really care right now. So let's just not print this, the individual automatons. Let's just print the resulting, the DFA. And what do we do? Yeah, let's just try this out, I think. Let's see if we get a automaton. Oh, this is not correct. What are those? And I'm printing them incorrect. So why? I think they're most characters. So those are all characters. Why is each label? But I think this is correct. By construction, since it is deterministic, I think this is correct. So let's maybe work on printing those character ranges a little more compact. How can we do this? So our character set as a format, a formatter implementation. So and here I'm just going to print, just printing every character. Does this escape method not include the slash, or doesn't? It doesn't contain it, so I'm just going to fix it. So if we print a just going to also include the slash. Oh, so no, wrong position. I have to start here. So okay, so now everything should be taped. No. So I allocate 12 characters. The first one is a slash. The second one is a U. I think I have to patch it here as well. So then I'm SN printing and skipping first 2 bytes. And this is only 10 since we only have okay, works correct. And then of course we give it buffer and the characters which snprintf created plus 2. I think now it should work. So this is now a better printout. And I don't know why this prints this. Maybe I can I convince it not expand it to a 30-bit tune value? So this is a character. Can I just do and FF? Does this now work? So it is a character, not an X. So now I fixed the print. Perfect. Okay. Now, how can I do this a little bit more compact? Do I have to construct ranges? I have to construct consecutive ranges and print those. Okay. So let's change the way we print this. So let's do internal helper, which just emit. So this gets a, let's give it an U8. And we are just going to put this one here. So this code gets printed. The character set contains this character. We're just going to emit. So C, and let's change the C to a U8. So we have to capture first by reference here. And escape is defined for characters. Let's change it back to U8s. So should be fine. And now instead of always emitting, so let's just try if everything works as before. Okay, seems like it. Now let's not always print. Let's just call this one. I think I'm just going to rename this once again. And I'm using a little helper struct, which I'm calling range. And we have to find basically we have to create ranges. And then I'm going to emit ranges. So I'm going to change my code, accept ranges, and then I can change this code as follows. So we are printing a comma if we are not the first, and else we're going to emit the range. So we format range dot first, then we print a minus, and then a basically the same thing again. So we then format the last, and then another quote. So then we are emitting ranges in the form A to Z, for example. Of course, now I have to create ranges. So let's do this. Okay. So, and here we are going to remember which one we saw last. So last. So if last. So this method is called which character, and we basically have to extend the range. So what do we have to do? If last, let's just check. If last is 0, I don't know how to start. So if last plus 1 is equal to C, then we are fine, basically. Include C in current range. Else, we commit this range. So from we have to also remember so let's just store it as a range. If current, so let's rethink. Let's rethink this. If current last plus 1 is gleich C, equal to C, then current last equal to C. So then we just extend the range. If it is not the case, we're going to commit this range. So emit, so this method is called emit, not commit. But we are just emitting the current range and then setting the current start, not static cast, the first to C and the last to C. So in this, what we're always doing, so I'm just going to do this instead, and I then can just invert the expression condition. So, and let's also initialize those. Yeah. Let's see if this works. Okay. It doesn't really work. I think I have to. Now I just got a so let's rethink this. I think I can handle this. So basically we get ranges. So are those two bounds inclusive, or are these exclusive? I think the first one is always inclusive. Second one, no, both are. So let's then maybe check an empty case. So basically, if we extend our range once, so we set our current range to false. So in this case, we extend. Maybe I just have to. So something went wrong. Somehow the indentation get completely messed up. So I'm just going to revert So let's see. Let's redo this code. I have to rethink this, sorry. So if our last plus 1 is equal to C, then we just extend. So, and in this case, we're just going to extend our range. We also flag our range as non-empty, and else we commit our range, then we reset the range. So first of all, we set our range to a new range. Then we just remember the first as C, and I think the last one as C. Well, let's keep it like this, a little bit more explicit. But in this case, it is flagged as empty. So I don't know if this is right. So now our range is empty. We're just going to skip emitting it. So this doesn't work. Why doesn't it work? I think I have to do it a little bit differently, not with the empty hack. So let's just remove it. How do I? So if I print this now I have those dummy ranges, those 0 to 0, for example. Yeah. And I also have those, I have them everywhere. Oh. Also, I think I have to omit the rest, but not always. So now I have a lot of those empty ranges. How can I filter them out? So let's see. For example, here I have a character set from A to Z. That means that we have basically we have a range from 0 to A. Let's write it like this, from 0 to A, to the character before A, which is a map. Table. So A is, why is A? A is 97, so 96. So let's say the character before, so let's just say, just for me, just going to include the number here. So and then, so we have this range, which is the empty. We should skip those. So how do I compress those? So this method is called with each character which I should print. So if range is 0, 0, so this, why is this so hard for me? So this is called with each character, and I'm checking if they see the next character in the range. So if last plus 1, if this is the case, then we extend the range. Else we omit the old range and reset our new range. So let's just run it and see what actually happens. So now we get called with an A. I committed, though it can be 0. So A is the first range. So I have to extend once, be non-empty. So I think I'm going to reintroduce my empty hack. Range is empty, then return this semicolon, the wrong position, and then so we are meeting our range, but it is flagged as empty, so we skip it. Then we reset our range. And remember that A is our first letter that we see. A to A is a valid range. So then we see our next character. So does this work now? I don't think so. Okay, so now it all still prints empty range. There must be another case, which I'm forgetting. Also, this one will break all of my tests, but okay, sure, will be a little bit more clean in the long term. So my character set, let's just work on a separate test case. So I have a char set from A to the 4th inclusive. So let's just return and debug print our char's character set. Okay, it prints an empty string. So let's just print something before and after our set. Okay, but we see that it prints nothing. So how can we fix that? what can we do this better if we inline this here? Or let's inline this method. Oh, this emit, of course, must be. Did this fix the problem already? It did it. Well, derp. But does it now work? So let's also include pass set. Let's just set the 0th thing and also set range A to Z. Does it print correctly now? No, it does not. So that is unfortunate. But what happens if I also in A to capital Z, for example, and let's also underscore. Okay. So the ranges work, but the single characters don't really work. Yeah. So, but I think I can fix this when I inline this handle helper. Yeah, so I didn't want to do this. I can just drop the call here. So okay, sure. Now, if we should print it, so in this case we need to print out. Now we have two different cases. So if current last plus 1 is, then we have to extend the range. This works. Also we got to reset the range. I think I have to handle a special case if current first equal to current last and current first not equal to C. In this case, single character range. Just marking it as non-empty. Ah, well, it does not work. Perfect. So I think this one always happens when we reset. And I just check anything. Can't I just say empty is false in this case as well? So we just ignore the first empty range. This work. Almost. Oh, it works. This is what I expected. Wait, it works. Finally. Well, I didn't know why this is so hard. So 0, 0. But what happens if I remove this? Main. Let's just remove this first singleton range. I think it works. Perfect. So A to Z uppercase, then a like underscore. So now I can also simplify this. So if the range is empty, we skip it. Comma separated. I'm going to spend a space here. So I'm, of course, breaking all tests. I collapse those into ranges, but I think this is fine. So I can also spend another space here. So, and I can special handle if our range first is equal to our range last. I can print it a little bit different. So in this case, I'm just going to print single character. So just remove this. Yeah, so just a single character. It doesn't matter if I print first or last, since they're equal. I think I can refactor this. So I'm always printing the first character. And if first and last are not equal, I can just print this. So now I think the singleton ranges should be printed a little bit more cleanly. Oh? Yeah, so it works. So, but now let's reintroduce our 0 print and also the dummy strings around our character set. So I like this. A little bit more clean than the whole character range. So maybe I'm just going to commit this individually, but let's also resurrect our tests. So let's rerun those, see which test fails. So this should break almost all of our tests. Okay. So now it would be great if our tests showed positions in our source code. I think not work on this yet currently. So this is now this is A to Z. It's a lot cleaner. In this, instead of this mess, it is A to Z, comma, A, E. Closing parentheses, like this. This one prints, well, here the space, with the space. This one is just 0 to 9. And this should be it. So it's a lot cleaner now. I like it. I really like it. So let's commit this individually. So what did we do? We introduced a lot of stuff. So I would like to commit the character range thing first. And also we changed this. I think we're going to commit this as well, since this related to the character set print change. So what did we do? The rest of the program. Okay, a lot of things we didn't commit the last time, so doesn't really matter. Change how char sets are printed. Instead of printing individual character successive consecutive. So let's learn some English, shall we? Let's try. If characters are collapsed and printed as ranges. So I think this is a great commit message. So let's let's do some more committing while we are on it. So this one is just introduce list contains. So then let's just add our set first. Introduce core.set. This is the most. This class defines a simple API for a set currently implemented using our lists. Of course, this will have to change later. So now let's commit our map as well, which is similarly stupid implemented. Our map. This class also only defines the API implementations So then args don't store their states immutable as const pointers. I'm just going to commit this one as well. I think the other changes are completely unrelated. Let sigil NFA arg for its state. Simply. Don't know how to say this. Drop const qualifier of args members. So this should be enough for now. So now our tests work again. Also, let's rerun our program and keep going. So I think this now works. So now the edges. So now we list all possible edges from each state. So this is a deterministic automaton. So each possible transition listed. So let's draw this automaton and look if it actually is right. I think it is not really right. Correct. But let's just, well, I don't need the ASCII table anymore. So let's draw it. Our first state is state 0. It is the first state and it is accepting. Sure. Then we have a transition. But why is the first state also? Why are all the states start states, this is not correct. Can't be correct. I did walkie. So here it is. So I copied much. I already found a bug. I just copy and pasted this code block, and this is only correct to do when we are looking at the start state. So now it looks a little bit better. So let's continue drawing. So the first state is a accepting state. Then from character 0 to from 0 to hectic, or what? This looks like a great smiley. And also from C to FF. I don't know how to write this. So this is the whole range except A and B. I'm thinking of drawing this a little bit different. So I'm going to label this as a class, a negated class. Basically, I'm going on, also just here for visualization, I'm just going to describe this transition as negated A and B, since it is a little bit more readable than string. So we reach state 1, and from 0 we reach state 2 when we reach 3 B, and we stay in state 1 with everything. So I'm just going to write this by a dot. Means a regex dot matches any character. From every state. So if we see any character from 2, we reach 1. Okay. 3. Okay, 3 has 2 possibilities. CAB, we stay in 3. And of course 2 is accepting. We are in 3, and CAB, we stay in 3. But if we see a negated B, basically we go to 1. So drawing this a little bit weird, but this means that 1 is, I think 1 is the explicit error state. But how did this work? So what does this automaton, what can this one accept? It accepts, so what are the tokens I gave it in those 2 tokens. So, and I think accepting state 2 yeah. But how does it work? So I think it didn't quite work. So let's just go through it. Just use a color. So if we, for example, want to pass, let's look at what happens when we pass an empty. So an empty string should be fine. We start at this state and we accept. this is fine. But now, what is the problem is that those two tokens accept the same inputs. So in this case, since this token was defined earlier, I would expect that this state associated with the first token. So let's just I don't know, let's just say this one is labeled with the token A. So this state, if this state accepts, we return token A basically. This one as well, this one is labeled with B. So I think this is the expected behavior, but what it actually does is, so we don't currently do this labeling, so but what I would expect, of course. So okay, we accept, so this is fine. Let's follow what happens. For example, if we have a single A, we start here, A, and we reach state 2, which is accepting, which is fine. Okay. Okay, so this is also okayish. And if we are in 2 and see another character, we reach an Aerostate. But where does this state come from? I'm going to have to analyze this a little bit more thoroughly, I think. So, and if I B, of course, this regular expression also allows empty tokens. So in this case, also this state would accept. So yeah, so I have to do this labeling thing, I think. But if I see a single B, I reach state 3, then I'm accepting, and I can stay there and consume more Bs, and if I see something else as reaching Aerostate, yeah. So, but where does this state come from? This is magical. Maybe I don't have to write the whole range. I know what this causes. So let's see, where do I here I iterate through all characters. So what happens if we actually, let's just comment it out, and let's just replace this by a, let's iterate through all used states. And each state how is this defined? So the state, I don't know the outgoing characters. So I think I can do the following thing. And this is the NFA states. So I can iterate the arc from our NFA state from our automaton. We iterate the arcs, and if our arc source, our origin, so basically we find the outgoing edges. So the NFA state outgoing edges from our state, And basically I have to introduce another scope here. I would like to repeat my assertion, this one. Since I'm abusing this fact, so arc, the arc is either an epsilon arc or a character set arc. So, and then of course I have to add another for loop, which iterates over the whole range, but also works if arc character set contains this character. So I'm converting this and doing an early return. Continue. So this is a little bit more nested. So this is the only. This is so horrible. I'm thinking of rewriting this. So basically, the idea is this way we only look at the transitions which are actually defined by our NFA state. We're doing this by iterating all of our NFA states, iterating over all arcs. We're iterating over all arcs. Which are no epsilon arcs. So we're iterating over all reachable, all outgoing transitions, and just look at the character line. So I think this way we eliminate the explicit error state, but I don't know if I like this better. So I think this automaton is much cleaner, and other transition is an implicit error. Oh, but can I do this a little bit different? Oh, I think this is quite messy. I think I'm keeping it since it produces a cleaner automaton. Or can I somehow attach? Can I attach the information that a state is an error state? I think I can do this. And this would be even cleaner. So I like the idea that we have an error state which is explicitly encoded in our automaton. It's quite messy. So let's keep this code just for reference. Maybe I'm going to switch it to this one later. But for now, we're just going to use this. So I think I messed up indentation. So here in parentheses is missing. Now it should work. So let's just keep this. So now we have an explicit error state. And somehow mark this. So I think I have to mark it like this, but then I have to remember that this state is. So I think we will do this. So I like the resulting automaton where we explicitly have an error state yields this automaton. The operation yields this automaton, which is not as clean as the other one, but of course, yeah. So it's I like it. I really like it. So then, of course, we have to remember that, let's say, flag explicit error state as error state, and also we have to do label those. So label tokens, label accepting states. Remember which token they represent. So I think those two things we're doing next time. I think I'm just killing this code. It is horrible. I know I said I'm keeping it, but not keeping it. So now it would be great if I don't have to draw the graphs. Well, but it doesn't really matter. But let's just have a little sneak peek what happens if I uncomment the rest of our tokens. How big does the automaton get? So we have 19 states. It's quite messy, but yeah, I don't have to do this by myself. This is great. So I think this is really easy. The error state is when I know what the error state does. So basically, this is the empty set. So if reachable is an empty set, this is the error state. Reachable is empty. I just found this out. I think this is why we always get the empty set. Since this state is not reachable, yeah, so if we reach no character by transitioning via character, let's say by digit 5 as an example, and we find these states reachable from this one. So basically, if this set is empty, which we get back here, and this set will also be empty. So in this case, reachable will be empty, and we will, using this code, we will explicitly create the error state. So this code implicitly creates the explicit error state. So in this case, we also have to remember this, that this is the error state. And for this, I think, yeah, so I'm thinking that this should be fine. So, perfect. And then I think we are almost done. When we have a DFA, we can simulate this. Also, already start scanning, but interpretively. So, yeah. So basically now we have a full DFA. So I think I'm just committing everything we done today is in commit to just do everything. Turn NFA to DFA. Let's say convert. So what do I want to say? Turn a, well, it's not called MFA, it's called NFA, a non-deterministic finite automaton to a deterministic one by subset construction. We still the main algorithm needs to work. We need a way to unit test it, something like this. And of course, there are several things to work on next. We have to remember which state is the explicitly generated constructed explicit Aerostate, and we have to remember the token which each accepting state accepts. Does it make sense? We have to remember which for each accepting state, we have to remember which token it accepts. Does this make sense? There are several things to work on next. We have to remember which state is explicitly constructed explicit Aerostate. This sentence makes sense, I think. And for each accepting state, remember which token it accepts. Yeah, well, not perfect. We made it a little bit better, but I think it's understandable and clear enough. So, okay. But I love that the main algorithm already works. So this went really smooth today. Sometimes a cup of sleep really works. So I wasn't really concentrated last time. And using this approach, of course, we allocate everywhere. So let's keep some more nodes. So optimize allocations. For example, using Arena. Of course, we have to optimize our map and set implementations. They are horrible. I would like to work on unit testing. NFA, I'm not really sure, but I would like to unit test our DFAs. What did we wrote here? So I think those you have to remember this one. And I think I would like to create a different separate data structure. Different data structure for DFA. So currently I'm abusing NFAs, and since I have to remember which state is the Aerostate, so the DFA, the MFA doesn't really, so I construct the MFA in a way that there are no explicit Aerostates, but if I now remember this, I have to extend the data structure, and I really don't think it is really clean. And also the DFA has the notion of epsilon transitions currently, since, well, I'm reusing the Nfa data structure. I don't really love this, but so I'm not sure if I would like to do this. So I think we did some great progress today. I think I'm just going to amend those couple of comments and think about them, and we will continue another time, since I'm really tired and I gotta eat something. But I'm glad that everything worked like a charm. So thanks for watching. I hope you had a great time. I sure did. And yeah, hoping that this is somehow entertaining. At least my mumbling and my really great English with a German accent. So thanks for watching. Have a great day. Bye.